Greetings, Gallatin Valley, listening on KGVM 95.9 FM, and to the world, listening on KGVM.org. This is Health and Happiness, a program focusing on, you guess it, health and happiness. While mental health issues are our primary topic, today we have an area that is truly universal in nature. I am Dr. Arlis, Wood psychologist, along with Dr. Suzanne Wood, speech-language pathologist. We thank Bob Wall, radio and computer engineering guru, and the Public Education Committee of the Montana Psychological Association for their support. Dr. Suzanne introduces our special guest and topic.
What benefit to us does education provide? Why is science our friend? How does our mind or brain respond to training, education, and huge mental or cognitive effort? One study was able to find a sample of cognitive measures that spanned a lifetime. It was called the Nuns Study, a group of ladies who stayed in the same convent for all of their lives. The researchers looked at written language samples of the nuns taken in their early 20s. Then they measured again in the 70s and 80s for those ladies, and they found that those who had high scores on grammar, spelling, and correct language usage fared much better over the years. They, unlike the many others, did not develop the symptoms of Alzheimer's, even though some of them had the plaques and tangles that are associated with Alzheimer's. The researchers concluded that the strong cognitive effort and high level of skills involved in language learning was protective. Using and protecting your brain is healthy and can happen at any time of life. We'll talk more to that later. And speaking of brains, today we have with us an actual rocket scientist from our own Montana State University, a person whose efforts will benefit our world and will protect his brain forever. Dr. Brock LaMeres, who has led a team of workers to develop a device that NASA is taking to the moon. Welcome, Dr. Brock. We'd love for you to tell us how you began this journey to the moon.
Well, thank you for having me on. It's always exciting to talk about what we're doing here at Montana State University. So I've been here for 17 years, and when I first came here, I was interested in just trying to make computers run better. So making them run faster, making them do more complicated things. And some of the initial ideas that I had that I was playing around with caught the attention of NASA as a way to make computers reliable. And I had the opportunity to start talking with some engineers at NASA about my ideas, and they started telling me about the issues that computers have in outer space due to radiation from the stars. And I had never even thought of anything about space radiation or putting anything into outer space other than just always being enamored by space and the space shuttle program and growing up as a little kid wanting to be an astronaut. And it was very exciting to talk to them about the potential to kind of start doing research at MSU on this idea of building computers that could operate in outer space. And what ended up happening was we came up with an idea, which later we named RADPC, which was a computer technology that implemented redundancy. So multiple computers where if one was caused to fail by radiation, the other ones could pick up the slack and continue running while we went in the background and actually repaired the faulted computer. And this idea then garnered some funding from NASA to try to start, building a prototype. And that then led to another project to try to test this in a radiation chamber while we were in a laboratory and shooting it with radiation to see if we could continue operation. And once we got through that, that was probably 10 years ago, we got our first opportunity from NASA to actually fly this, because they said, you know what, if you're going to build something for NASA, you can't just test it in the lab. You got to fly it. And so we started flying our computer on high-altitude balloons out of Big Timber, Montana. And so we started doing that for a couple of years, and then that led to another project to try to fly it on what they call a sounding rocket, which is one that just goes up and comes down. And then that led to actually being able to go on board the International Space Station and test our computer there. Then we were able to get a project to fly some small satellites carrying the computer. And that has led to the most exciting project yet, which is an opportunity to travel to the surface of the moon in 2024 to demonstrate this computer technology that's been in the works at MSU for over 12 years.
That is truly fantastical. I bet it's even hard for you to grasp that is actually getting to happen.
It is, especially when I go look back at the pictures, because we try to tell the story of this computer. And I always go back and I show pictures of students working on it, over a decade ago, and driving around, the fields of Montana, trying to search for where the balloon came down. And it's remarkable to see what form it took back then and what it looks like today, where it looks like a real space, technology that we turned over to NASA. And to think how long it's been. On some days it feels like it's been an eternity since I've been working on this, and other days it seems like just yesterday we got our first grant. So it's been just a phenomenal experience.
And for our younger listeners out there, you said that all of your life you'd kind of looked toward the sciences, some of these directions you wanted to take your life. Were you interested in space as a 9-year-old, for instance?
I was always a fan of the science fiction, TV shows and NASA. Growing up, I always watched Star Trek and Star Wars and loved that sort of stuff. So I was always enamored by space. I never really thought about becoming an engineer until my older brothers started talking about going to college and what they were going to major in. And so that was kind of the first time I'd really thought about becoming an engineer myself. And then I took a physics class in high school, at Billings West High School back in the 90s. And I had a physics teacher that was extremely inspirational, and that really lit the fuse. And I said, you know what, it seems like a viable opportunity since my brothers are heading down that path, so I give it a shot. And that started kind of my educational journey of becoming an electrical engineer.
Could you give us just a thumbnail sketch of the kind of training you needed and all that brain work you had to do to reach the point where you could begin to address actually making this computer?
Yeah, it was a long journey, although it went by in the blink of an eye. So I graduated from, Billings West High School in 1994, and I first went and tried to play baseball at the University of Wyoming, and I went down there for a couple years, and then I returned to Montana State to complete my degree. So I got my bachelor's degree in electrical engineering from MSU in 1998, and then I went to work in Colorado, and I worked for a company called Hewlett-Packard, which at the time was a very successful, technology company. They're the ones that make your printers and laptops. And I worked there for 8 years, and I was a design engineer, and I got to develop electronic test equipment for the computer industry. So I was able to work with companies like Intel and IBM, and I wasn't building computers, but I was building electronics that helped them build their computers. And so it was a really interesting experience to see how much, work and how much of an industry is needed to get to the point where you actually can build a computer and ship it to somebody and they can write a letter and print it. It's just incredible. So when I worked for Hewlett-Packard, I decided to go, nights and weekends and start working on my master's degree. And I did it as a way to just better myself. I just wanted to be a better engineer for Hewlett-Packard at the time. And so I ended up getting my master's degree from the University of Colorado while I worked full-time. And then I had an opportunity to teach a night class for the University of Colorado. And they asked me, they said they were short of an instructor. And I said, holy smokes, I've never even thought of teaching. So then I taught this night class, and I just fell in love with teaching. So then I said, you know what, maybe I could find a way to make teaching part of my professional life. And one way to do that is to become or to get your PhD. So I ended up continuing to take classes nights and weekends at the University of Colorado and eventually got my PhD. And so now I worked in industry for 8 years. I had a PhD in electrical engineering, and an opportunity arose at a faculty position at Montana State. And we jumped at the opportunity to come back to Montana. And I got here and was trying to find my way in terms of, what can I do? And I loved computers. I loved, teaching. I loved working with students, and I was just trying to find, how I could help, basically society of how can I make better computers. And then the NASA opportunity arose, and that set me on a path that, 15 years later, we're getting ready to go to the moon.
How did the concept of radiation causing damage evolve?
It's interesting because stars give off radiation. So, they're basically big nuclear bombs going off continuously. And they emit a lot of different types of radiation. And what's fascinating is that my background is not like physics or, not understanding the radiation in itself. So when NASA approached me, they said, our computers need to withstand a huge array of radiation effects. But there's one in particular that you might be able to help with, and that is when radiation strikes a computer and it simply causes the circuitry inside to flip from one state to another. So you'll hear people talk about computers, how they operate on ones and zeros, or binary. And this is what happens for this particular type of radiation effect that I work on, where radiation actually hits the computer and it doesn't damage the material. It actually just causes a 1 to become a 0 or a 0 to become a 1. And that can cause the entire computer to crash. And so what was interesting about that was that I was able to apply some ideas that I came up with that weren't really about the physics of radiation. They were more about how do you just keep a computer from crashing when a 1 becomes a 0 or a 0 becomes a 1. So I was able to develop these strategies at more of a logical level as opposed to kind of a particle physics level. So I was lucky in that regard because it allowed me to contribute. I've since learned a lot about radiation. Still, I'm not an expert by any means, but that's the way that I got involved in this whole radiation-tolerant computing area.
So the redundancy, as you mentioned, is the backup. Somehow when something goes down, if you will, briefly, something will click in that will give it a rest so it can be repaired?
Yes, yep, absolutely. And, and I did not come up with the redundancy. NASA had been doing that. The space shuttle had one of its primary computers did a 4-computer redundant system. So the idea was not new in itself. What I ended up coming up with was an approach to basically, in the background, go to the computer that had crashed and try to recover it without altering the other computers. And so the approach ended up being a little bit faster than what had been done before. And they said, you know what, let's see where this goes. And so that was kind of the start of it.
That is just fantastic. Finding solutions to a problem solving. We all have to do that every day. Actually, my doctoral research required measuring short-term changes in cognition or thinking. And how do you measure that? That's really difficult, just from one day to the next. How does that change? And interestingly, that's something that NASA had been concerned with, because if the astronauts go up in space, does that have an impact on their cognitive ability to problem solve and be alert? And so they developed a test using computers where you had two tasks with each hand simultaneously, and that measured, it was wonderful, it measured cognitive difference in short time frames. And they were kind enough to loan us that test for my doctoral research, which was looking at a medication that was designed to help kids with language learning disorders, and we needed to know, does it actually work? And so it's interesting how all of these problem-solving issues and these wonderful efforts have spun off into other parts of our daily lives that we don't even realize that came from the kind of thinking that you're talking about, Dr. Brock.
Yeah, it is. It's fascinating. NASA's mission is, it's obviously about science and exploration, but it's always to better life on Earth. And so, there's what you're talking about with the cognitive tests and the studies they've done on astronaut, health, mental health, physical health. But then on the technology side where I work, the idea is, yes, let's use this computer on the moon. Yes, let's try to get to Mars. But what are you going to do with it in addition to that to make life better on Earth? And so we always are pushed to say, can I take this technology and use it to make our nation's infrastructure more resilient? Can I make the power grid, less likely to go out? Can I help, water treatment plants avoid a cyber attack? So NASA is it's at the forefront of their mind that they want to fund this leading edge research, but they want to see it trickle down so that we can use it in everyday life on Earth.
I was reading about some of the ways they've managed that. They're among those who developed advanced surgical robotics, so that we use those now commonly every day, but that was kind of an initiative of NASA, and makes sense because if somebody needed surgery in space and you had the robotic equipment, then a surgeon on Earth could perform that surgery. And they also were concerned about microorganisms that contaminate food. And so Pillsbury worked with NASA to develop something that would eliminate that danger, and it's now used and required by the FDA. And one of the things I think pertinent to Montana, they developed simple portable water filters which had not been available before, that are now used worldwide, and you see lots of those up on the high trails in Montana. So there are many other things, but those are just a few, including world peace has been enhanced because 18 countries have now participated in the efforts to go to space as a team, as a group.
Yeah, absolutely. And then there's Velcro. No one ever.
Oh, I love Velcro. Yes,
that's the big one.
Other fabrics too, and that's fun to go into that whole development.
We're always reading about the effects of solar storms and radiation that might disrupt communications and satellites, and it sounds like what you're doing is right down that alley of what do you do when radiation causes things to crash?
Yeah, exactly. The hope is that this technology could be used, on Earth, because you're right. The radiation environment of space it's very it can be very frightening to think about what's going on, but it's equally amazing how incredible Earth is, the way that it protects us, this whole ability to have a magnetic field which can deflect space radiation away from us, the idea of having an atmosphere that whatever gets through kind of gets, it gets reduced in its energy before it hits us. The Earth is it's an amazing place to live, and it really does protect us. But at the same time, these natural phenomena happen, like solar storms, and they've always happened since the beginning of Earth and the Sun. But now what's different is that human beings rely on technology for every aspect of their lives. And so it's no longer where you might use a technology as a luxury. It's now our technology is part of the human existence. It helps us with food, it helps us with water, it helps us with communication and health. So if these solar storms happen, we need to have a way to keep our technology running because it is essential to modern civilization.
Exactly. I love the mind that first discovered and was able to understand what a magnetic field is. My understanding of it is you can't see it, you can't feel it, you can't taste it. I mean, how inquiring minds like yours have achieved these landmark helps to our world. We should all be amazed a lot more often, Dr. Brock.
Yeah, I agree. I mean, human curiosity kind of keeps it going. And one of the great things about, the whole scientific process and what happens with the exponential increase in technology capability is that when somebody has an idea, then there's 10 other people who take that idea and advance it. And then each one of those has 10 people that advance it. And so you see this exponential, because what's fascinating is if you think about how long humans have been in our current form, it's been a long time. And if you think about how long computers and electricity has been around and automobiles and wireless communication, it has not been very long at all. And so it's just been a snap of the finger in terms of how long we've been here that we have technology and how it's gone from, wow, that's really interesting, to it's embedded in every aspect of our lives now.
I remember typing the last dissertation that was hand-typed at the University of Oklahoma just before computers came bursting upon the scene, or at about that same time. But mine was the last one where you had to use carbon paper and triple copies, and then if you made a mistake on page 40, you had to redo the whole thing to the end from that point. So just within my lifetime, Dr. Brock, we've seen so much change and improvement.
Yeah, it's incredible. It's my dad was a computer programmer early in his career, and he did it with punch cards. So he would have a deck of papers, and he would punch in ones and zeros by punching holes in papers and run it through a machine that could then read those ones and zeros. And I mean, to have a program that was hundreds of bits or hundreds of ones and zeros was a big deal. And now with one line that we type at a computer, we can generate, billions of ones and zeros that are executed on a computer in unimaginable speed. And it's just incredible. And that is within, one generation that we've seen that exponential increase.
It's incredible.
What you remind me of is back then, Suzanne and I were about the same age and both finished a dissertation. And the size of the machines in the labs were amazingly big. And I'm aware that the device that you have contributed to making is much smaller. Can you tell us about that?
Yeah, I mean, the first computers used to take up full laboratories of space and had hardly any computing power. So now the computers that we're developing on a single, what we call computer chip, which is, no bigger than a half an inch by a half an inch in, dimension, that thing can hold 4 full computers. And I mean full, like it's got the central processing unit, all the memory that it needs, and we have 4 versions of that, and we still have room to spare to do all sorts of interesting recovery procedures. And the computer that we fly, the chip is that big, and on that chip are literally billions of transistors that are as small as a nanometer, or 22 nanometer is the smallest transistor that we are currently using on our RAD-PC computer. So they're sizes that they're unimaginable, they're untouchable. You have to alter them using light instead of actually mechanical, contact. And so it's mind-boggling to think about how small we make these things, and then it's equally mind-boggling to think about what we do in replicating those little small transistors and how many we put together to create a billion transistor chip that then we can run full computers on, and not just one computer. We'll do 4 computers, and then we'll put that inside of a small box that has even multiple computers on top of that. The computer that we're sending to the moon, it has 4 computers in it, one of them being RAD-PC, but we also have 3 other computers in there that handle housekeeping, like taking measurements on the temperature and how much power we're using. So it's really interesting, the scale of how small things are to how large of quantities of the transistors we can get to.
I think the picture in the newspaper or in the articles is they call it the size of a Rubik's Cube.
Yep.
That is so mind-boggling. Well, I loved the transfer story when you were going to take the device from Bozeman down to NASA. Could you kind of tell everybody that story?
Yeah, it was pretty interesting. So we developed our moon project, our moon computer, and we had to deliver it to an aerospace company in Austin, Texas. And the computer itself, the way that it worked is it was technically became NASA property as soon as we signed a piece of paper in Bozeman, but then we had to deliver it to Austin, Texas. And here's this computer that we'd spent 3 years developing, this particular payload that is literally the size of a Rubik's Cube. And we were very nervous about the airport security because we had to build this in a clean room facility so that it couldn't be out in the open, or else it would get dirty and we would have to then go through a huge procedure when we got there. So we had assembled it, we had done all this testing on it, all this environmental testing and cleaning, and it had not been in like a regular environment for many months. So we had it all packaged up, and we put it in these things that look like basically look like little briefcases, but they're padded and very secure. And NASA provided us with these big red stickers that said, sensitive space equipment, do not open in a regular environment. If you need to see into this, call this number. And we gave them the phone number of our NASA mission manager. And my students, I ended up not being able to go to Austin. So I had 2 master's degree students. I had a master's degree student and a PhD student who pick up this suitcase in the lab, and we took a picture of them holding the suitcase, and they headed out to Austin. And we were all in the lab waiting to get this phone call from them saying that airport security wanted to open it up, and what were we going to do? And so I was ready to race to the airport, and I had our mission manager from NASA on call. I'm like, if they call, make sure you're at your desk so we can do this. And it ended up they just walked straight through security and got on the plane, and there was no issues. And it turns out that our computer just looks like any other computer that everybody else has in their duffel bag, or their backpack. It just looks like a laptop when you scan it with X-ray, and it caused no concerns whatsoever. So they got there, and it was a huge sigh of relief on our end.
That's an incredible journey for that amazing little box. I was just wondering, you mentioned all of this. Have you ever thought of personally going into space, Dr. Brock?
I have. I'm getting a little old. I don't think I'll get on a NASA mission, but space tourism it's a really fascinating concept. I mean, I think I would go on one of these, up and coming ones. I'd probably wait till they're a little bit more mature, but some of the interesting ones are, these capsules that fly on high altitude balloons, where if you go up to, let's say, 100,000 feet, you're in the blackness of space. So you're not technically in space, but you look like you're in space. So you have gravity, but you see the curvature of the Earth, and it's black. And we learned that. I mean, everybody's always known this, but that's how high our balloons will go. So when you take this balloon and go up to 100,000 feet, you're in the blackness of space. So when you take pictures of the computer, it looks like it's in outer space. And there's tourism companies that are emerging that will have an experience where you can fly in a capsule where you'll go up and it will feel just like you're in outer space other than gravity in terms of the view. Then, of course, you have like Blue Origin and Virgin Galactic, where they will take you up into outer space and experience no gravity just for a few minutes, which would be amazing. So I would be up for one of those. I don't know if I could make it into the space station, though. That would be pretty intense.
Well, I think you deserve to get to go after all of your work. I was wondering, too, I understand that you have started a company that has to do with some of your research work.
Yes, 2 years ago, I started a company in Bozeman called Resilient Computing. And the idea was, at Montana State University, we are doing the research and the development of the basic computer idea. And we mature it through different flights, and we get into harsher environments, and it becomes more and more mature. But at the end of the day, it's always a university experiment. So it's not something that anybody could ever come to Montana State and say, I'd like to buy one of those, because we really only build one at a time. And it's never really in a form that anybody could use practically. It has to be held. I always say it's held together by all my graduate students with bubble gum and duct tape. And every time you have to change the software, they have to pull the whole thing apart, get inside of it, change the software, and then put it all back together. So we started getting a lot of interest from, big companies, the big aerospace prime companies. And they were interested in it, and they said, I would talk to them, and they would always kind of go away and say, we love the technology, but, it really has to take another step toward being in a form that's more like a product as opposed to a university payload or a university experiment. And that's when we would then get engaged. So I worked with our tech transfer office at MSU, and we kind of crafted this idea of, why don't I start a company called Resilient Computing, and I will license the technology from Montana State. And then what I'll do is I'll try to go after some of these small business grants that NASA and other agencies have that allow you to take technology from a university and basically spin it out and try to make it into a commercial product. So I was fortunate enough to win a couple of these grants from NASA, from the same people that were funding the research, but it was more focused toward businesses. And me and my PhD student have been kind of working on this on the side, trying to make the technology into a form that somebody could come up to it and say, I'd like to buy one of these. I realize it's not quite there yet, but I can see that it's a lot closer than it ever was in the university laboratory. So yeah, Resilient Computing, Bozeman-based, part-time employees. We've got a few part-time employees trying to turn this research into reality, and hopefully it'll keep growing.
Well, I was just going to say, Dr. Brock, I've had a little trouble with my laptop lately. Can I just bring it by and have you look it over? No.
I'm probably not the right person to do that.
I couldn't resist that. Sorry. I was going to quote you that at one point you said, we hope it can help in building the lunar ecosystem that will sustain a human presence on the moon. And so my question was, if you could tell us a little bit about how you think it might do that.
Yeah, so if you kind of look at what NASA is trying to do right now over the next 10 to 20 years, the whole goal is to put a person on Mars, right? And so there's a lot of different ways to do that. You could just go straight there and not come back. You could try to take everything with you. And the leading idea of how to get from where we are today to where you have potentially a colony on Mars is to use the moon as a testing ground. So not just go to the moon and get off and collect samples and come home, but actually build habitats there and actually have people live there. And the idea is very similar to the International Space Station, where we wanted a presence in space and we wanted to study what are the effects of outer space on the human condition. You know, what does it do to their mental state? What does it do to their physical state? And we've learned a lot about being in orbit around Earth. Now we want to learn about what is it like for a human being to live on another body that doesn't have the same gravity, the same atmosphere, and what does that do? How do you survive? What kind of supplies do you need? And what does it do to the mental and physical capacity of the human? And when you think about doing that, where it's a sustained presence, you realize very quickly that you can't bring everything with you in one shot. So you need to start going there without human beings and start building the habitats or trying to extract things from the natural resources of that particular body in order to get ready for humans. And so there's a lot of planning that's going on in terms of, can you send uncrewed robots to the moon in order to start potentially mining dirt in order to extract water from it? Can you start potentially building the basics of a habitat so that when the humans get there, they don't have to do all the work on their own? And so when you think about this idea of sending uncrewed, robots and technology to the moon, it's all based upon computers. So you have to have robots that are smart enough to, be able to do things on their own. You're obviously going to try to control them, but you can't constantly be controlling them. You have to allow the robots to actually do stuff on their own. So set them up to mine the dirt and let them go for a week and then tell them, okay, now do this with the dirt. And so the idea is that you're going to need a lot of computing processing power. However, the moon is not protected by an atmosphere, and it is not protected by a magnetic field like the Earth is. So those computers are going to be fully exposed to the harsh radiation that comes from stars, mainly our sun. And so when you look at NASA's plan with the Artemis rocket and NASA's plan to fund SpaceX's Starship, these are kind of longer-term vehicles that will carry crew ultimately, but also a lot of supplies to the moon in order to get ready for a sustained human presence. The moon mission that we're going on, the MSU Moon Computer, it is one of about a half a dozen uncrewed lunar landers that are going to travel to the moon before humans get there. And the idea is to test the capability of commercial companies to build these lunar landers and actually try to land them on the lunar surface, and as a way to figure out how to do the transport of it. Along with that, as long as you're going there with the lunar lander, you might as well bring along technology demonstrations. And so we're on a lunar lander that has a bunch of different technology demonstrations. There's one that can, vacuum up dirt from the moon's surface and put it in a container to analyze it. There's experiments to measure, the electromagnetic or the electric field of the dirt, how much resistance it has. And then we have the RAD-PC computer, which is an experiment to see how well our computer idea survives when it is struck with radiation that is not protected by the atmosphere, the magnetic field of the Earth. So if we can demonstrate that, there's a potential that you could use this computer technology in some of the future missions that are going to go to the moon in order to start building up that ecosystem so that we can have a sustained human presence on the lunar surface.
Whole lot of cognitive problem solving going to go on there.
For sure.
What happens if the device is an accident occurs and it is destroyed or impaired? Are you all able to reproduce, replicate, have backup systems for them?
On our mission, no. So our mission is, while we implement redundant computing, our redundant computing is within one computer box. And so if we fail, that's it. But luckily, this is a technology demonstration, so we're not performing any critical operations other than to test how well we survive. If we were doing something critical, mission critical, you would absolutely have redundant actual computer boxes. For example, the Mars Curiosity rover, Mars Perseverance rover, both of them, they have two full computer systems. They call it the Side A and the Side B, and they actually switch between them from time to time. When one of the computers will crash, they will shut it down and they will bring up their backup computer, and they basically switch back and forth whenever there's a failure. So in mission critical applications, you absolutely will double up on how many rad PCs you'd have on the actual system.
I was thinking about your graduate students and what they're equipped to do, and could you talk about how I'm sure it's something that many are applying to get into your program, and talk about how this benefits the graduate students and where their studies with this might take them.
Yeah, one thing I always remind people is everything that's been developed for Rad PC since its inception has been done by students. So I have never been allowed to write a line of software or turn a screwdriver. I am in charge of kind of working with NASA to define the projects and then hiring the students to get engaged and actually pull off the test or the flight demonstration. So as a student, it's a really unique opportunity because in the classroom, you learn the theory, and we do our best in the classroom to try to give them, laboratory experiences where they actually get to do something with the theory. But at the end of the day, it is a challenge because you only have so much time. When a student comes and gets engaged in research at a university, it can be treated as kind of like a part-time job. So students can, say, I want to work 5 hours a week or 10 hours a week or 20 hours a week, and they become part of a research team where, in my group particularly, we're not just working on ideas, we're actually working on deliverables. So they come into my lab, we have a deadline to deliver a payload that's going to fly on a vehicle, and everybody is focused on that. So they come and they're part of something that's bigger than themselves, but they realize very quickly that all the stuff we teach them in the classroom actually is important. It's not just stuff we're making up. It is actually what we do to build these computers. And so they get to apply that knowledge right away. And that helps them in turn in their classroom because they see why they're learning that information. And it helps their cognitive process because they see the actual application of it. So when we teach them the theory, they don't just shut down and say, yeah, whatever. They say, geez, I see this in my job. I see this in the research lab being used. And so I will pay attention. I will try to actually absorb this information. So then what happens is you have the hands-on aspect reinforcing the classroom material. But then they start getting taught how to build space systems. So they start learning it's not just about a computer for, another human like on Earth. It's a computer that has to go into space. So they start learning all the things they have to do to make that computer work. Keeping it clean, keeping static electricity away from it, the type of materials you can use and the type of materials you can't use. So the biggest problem that I have in my lab is these aerospace companies hear about what we're doing, and they come and they hire my students away before I can get them to go to graduate school, or before I can get them to get their PhD, because the companies look at this as, usually they hire a student who just has the classroom theory. They come to Montana State and they hire students that work in our labs doing the space science and engineering, and they get students that have had the theory, they've had the hands-on approach, but they've also learned kind of the first couple years of becoming an aerospace engineer. So they're extremely sought after because these companies say, I know this person can deliver space hardware. And so I have students, right now I have students working at SpaceX, at Boeing, at Raytheon, at Blue Origin. So every aerospace company you've heard of, they have recruited out of Montana State University, and these students go off, and I hear from them all the time saying, geez, we're doing just what we did in your lab. This is so great. And they send me T-shirts, and I send them Bobcat gear, and it's just really a cool kind of cool thing to see.
And they're getting good pay for it, I bet you.
And they are getting very well compensated for their skills.
You know, we talked earlier to the audience about using your brain and optimizing brain function, and that those who do so have great aspects of later life. I just wanted to mention also that I don't want people to be discouraged if they didn't make that effort earlier. I just wanted to point out another study that said learning a language is a simple way to involve your brain in extra complexity and build the cognition you need, and that learning a language late in life will help you to maintain and sustain good cognition thinking patterns the rest of your life. Just wanted to add that in for the audience out there.
I wonder if coding language, what you do in a computer, equals a different kind of language. I wonder if that would have the same effect. I guess we'll need another study on that one. So.
Yeah, it is an interesting thought, because a programming language, when students have never programmed a computer before, they have to understand, how do I communicate what I want to this other thing? It just has to be a machine. And so they pick it up, and it's probably similar in regards of there's a lot of just repetition of learning basic terms, and then you move to a higher level of cognition where you put concepts together to perform, to build a sentence or build a task. And so I bet there's a similarity between those two.
I guess I see your program, there's a dichotomy between cognitive function or cognition and what we call metacognitive, which is, I kind of think where you are, Dr. Brock, that cognition means you're involved, you're learning, you're working, you're doing all of this. Metacognition is your overview, looking down at all that you're doing to say, how am I proceeding? Am I going the right directions? What else could I be looking at? How can I keep growing this concept? And so I think what Montana State has achieved with your help is this great metacognitive overview of where we want to go and what we can achieve if we work very hard.
Yeah, and what's really interesting or kind of exciting is to watch students who come into the lab as undergraduates and watch their transformation, especially with regards to metacognition, which is where they when they first come in, they don't know what the project is. They just want to help, and it takes a lot of training to tell them what's going on, and then the tasks they do are very point oriented. It's like, do this 100 times. And then as they move through, especially as they move into graduate school, and then especially when they become PhD students, you see this transformation where they're no longer just about, the computer needs to do this, I'm going to design it. They start thinking about, what should the computer be doing in order to meet the overall research goals? And so as you get the opportunity to work with students that make it all the way to a PhD, and by the time they're a PhD, they're basically overseeing the lab, overseeing the research, and overseeing undergraduates underneath them at a much higher level where they understand the greater kind of place that all this research actually fits into, kind of the human condition and why we're actually doing it, why it's important, and how you get there. So that's been a really rewarding part of being a professor for me, is seeing that transition from the individual contributor to kind of the person that sees the larger picture right before they graduate.
What you're doing reminds me very much. We have a son-in-law who's an ER physician, and he, in his work several years ago, noticed that in his work there was a breakdown in the communication among all of the different parts of treating different kinds of, especially strokes and heart attacks. When they came into the ER room, that the time was too long to be of value to many of the patients. So there are some people like yourself and like he is that look at it and say, what if? The curiosity wonders, well, what if we did this? Or how could we make this better? And he put together a communication system. He now is Pulsara, Pulsara.com, in which he has developed a company and a system that coordinates and shortens the time between when the first symptom occurs, the ER people get the patient, and treatment is instigated, and has reduced it like 40 or 50%, which of course saves people. And your work saves machinery, saves people, develops a path for the future in space exploration that couldn't occur if without these types of processes.
Yeah, definitely.
So your curiosity is a blessing that you looked at something and said, hey, what if? What if we do this?
Yeah, it's like, again, that metacognitive overview that has persisted throughout centuries, but is now hard at work in the labs at Montana State. We would like for you to, if you could, give people a link to reach you, Dr. Brock, like email or at the university, phone numbers, whatever you would like to share, so that people interested in this work would be able to reach you. Could you do that, Dr. Brock?
Sure. My research website is probably the easiest one. It's just montana.edu/B-LaMeres. And so you can find all my phone number, my contact information, phone number, email, and also just an overview of the whole project and the history of what we've done with this moon computer.
We're getting down toward the end of the program. We have a few more minutes here, but this has been very exciting. I feel like I've been a journey person just listening to you. What thoughts would you like to share with us? What maybe concluding thoughts do you have about where we are and what you hope to do?
Yeah, I mean, with respect to the technology, the hope is that we can be successful on the moon and we can find a way to continue the research at Montana State in order to make it better. So if it's reliable, it's not done. It has to now do more faster performance. It has to do more advanced algorithms. So we want to try to really keep the research going in order to support NASA's plan to go to the moon and go to the Mars. And in parallel with that, we hope that we can try to use the spin-out company Resilient Computing in order to actually make the product form of this moon computer so that we can actually have companies purchase it and use it. And then, my personal hope with, the academics behind this is that everybody who comes to MSU who gets to see this or is exposed to it or gets to actually work on it is inspired in some way so that they can understand kind of the bigger picture of why we do this research, why it's important, and how important it is for them to continually develop so that they can contribute not just to building a space computer, but just like building kind of the infrastructure, the technology infrastructure that sustains our society, because it's becoming, there's more technology today than there ever has been. We need people to understand that technology and maintain it and grow it so that it can sustain society going forward. So I hope that there's some inspiration that comes out of it that manifests itself into a contribution to the workforce of the future.
Do you have any predictions on where AI, artificial intelligence, will be going in this area of looking into space travel?
You know, there's a big push from NASA to try to implement AI algorithms on computers. And when people hear AI, they always think of some robot coming to life. At today's form, it's really more about processing large amounts of data. So that's what artificial intelligence and machine learning is good at. That's what it's designed to do right now. And that's what you see in space. You have computers that just have a lot of different information that they must process. And our human brain is so powerful, and it's just amazing what our human brain can do. And to replicate that in a computer is very difficult. So AI and machine learning is an approach to trying to do that, where it would be very beneficial for uncrewed robots that go to the moon and go to Mars in order to process that information in order to, actually continue operating when there is something unforeseen that happens. I can't look into a crystal ball and say where we'll be with AI in 100 years, but I think AI is going to be very important in the next 10 years, 20 years, in order to enable these kind of autonomous systems to run continuously on the moon and Mars.
We ought to have the theme song from 2001: A Space Odyssey to end the program. I think that would be good. When I saw that movie, I considered it the best movie I'd ever seen at the time. And that was what we thought was, wow, 2001. This is 2023. Can you imagine what seemed like an impossible thing at that point is becoming more and more reality? And you're part of that. I think that is fantastic. Must make you really feel good.
Yeah, it's been a very exciting journey so far.
We're coming toward the end of the program. Any final words? Any final encouragements or thoughts?
Well, just appreciate you taking the time to hear the story. I think as a Montana-based, as a Montana native, I think sometimes when I travel around, I don't think people realize how cool the stuff is we're doing within our state, especially at our universities. And so it's always nice to kind of share what's happening at Montana State, because I don't think anybody would assume that this is happening within the state of Montana, but it really is. And this is just one example of kind of the amazing stuff that's being done within our state.
I, for one, am totally blown away, Dr. Brock.
Thank you so much for being on the program. We'd like to have updates, and we'd like to tell the audience here in Gallatin Valley, the 90,000 plus that are available to listen to this program, that you can listen to it on Monday evening, this coming Monday evening, or you can go to kgvm.org and review the program, listen to it anytime, and we're going to be sure that our grandchildren listen to it. So thank you for listening. KGVM 95.9. Listen to us Mondays and Thursdays.